Hello, everyone. So as he said, I'm going to get started, talk about replication history and grafting in the ORI file system. This is work we did at Stanford University. So let's look at users today. So think about ourselves. We have laptops and desktops. We have tablets and phones. We have lots of devices. And in aggregate, we have terabytes of storage. And this storage is really cheap. Yet somehow, users still go out and pay online storage providers $1 gigabyte a year. This is almost 25x the cost of local storage to take care of something, obviously. Another thing is that they go to enterprise storage at even higher costs. So what is it that users are missing that they have to go to these storage solutions and pay a massive premium to do something with their data? And what's missing really is that it's data management. The first thing is availability. Users don't want to worry when disks crash, when machines die, that their data is not available. They just don't want to think about that. Another important thing is accessibility. And if you think about like cloud users, you want to think that whenever you're traveling, you have access to your data wherever it is, whether it's in Pittsburgh or in the Bay Area. You have access to all your data information, everything that you really care about. Next is durability. Data should never get lost. So if I delete a file, I damage a file, I still want to be able to go back and pull an older version and recover that file. And our last important use case that users do is usability. And so you can think of this as collaboration and version control. This is something that users do today more than ever, and somehow we need to make this easier to do. So this is the goal of the ORI file system, is essentially to try to bring these benefits of managed storage and implement it on all the hardware you have today. And what we notice is that when we look at cloud storage providers or even enterprise storage, there's sort of two main usage models. So the first is personal storage. I'm a user, I'm going between multiple devices, and I just want to have my data accessible from those different devices. The other main model is there's shared storage, where users are collaborating with some form of shared storage. They might have to deal with conflicts and all kinds of other issues. So what are the problems, though, with these storage models today? So one of the main issues is bandwidth. We're limited by wide area bandwidth. Another important one is privacy. Do we trust these third parties to host our data? And next is, as we talked about, is storage costs. Storage costs are much higher than the cost of your local storage. If it's a 25x premium, maybe you can do something better with that. And lastly, we think it's a really important one, is poor integration. And if you think about it, we have sort of three main features. You've got replication, versioning, and sharing. And these features don't really integrate well. So if you have a Mac, you might have Apple Time Machine, which provides you backup and versioning. But that doesn't integrate in any way that I can export that info to some friend of mine. So if I wanted to email somebody a document, I can't give them the context of that version history. So what's the big idea here? What it is that we'd like to leverage trends. So first of all, we have big disks. Another thing is that we have really fast local area networks. And finally, we have mobile storage devices. So you think of phones, they have tons of storage, they have fast networks. It's a great device to store data on. But when we look at online storage providers, we see a fairly big problem. And what that is that there's basically a disparity in growth between your disk and your network. And so what we've plotted here is the growth in a log scale. And you look at it, your local area network for most people's homes has grown about 100 times in 23 years. But also in 23 years, the disk has grown about 40,000 times. And what this causes is that if you think in 1990, the average person could have uploaded their entire disk over a modem in 14 hours. But today, it would have taken 278 days to transfer all that information. So this brings us to ORI and basically our main design principles. So first of all, we want to store not just files, but also their history. We're going to take advantage of all that disk space to store files you really care about, files you spend hours and hours working on. These could be documents like PowerPoint, Word. These could be code, text files, whatever it might be. We also want to replicate files and their history widely across all our devices. We want to make this replication seem really easy to do and appear instantaneous. There's no master in ORI, so if any device fails, it's okay. The other devices just will have your data. We try to use your local area network speed and your disk space on all your devices to make replication better. And lastly, we want to use history for sharing. So Ori provides 4 main features. So the first is history. And we'll see how this kind of ties into everything else. So the second important one is replication, and we'll actually use replication. We'll use history to make replication a little faster. And next is recovery. And there's 2 forms of recovery. One is you recover from a whole machine failure by replicating from another node. And another is recovery from when a particular file gets destroyed or damaged. And our last thing is that we have our file sharing mechanism that we call grafting that shares not just the file but also its history. So now let's start talking about history. So this is just a little background matter for you to understand the rest of the talk. So SFSRO and Git, we've basically borrowed their data model to implement Ori. So we have a content addressable storage system where we store objects by the SHA-256 hash of their data. This creates a nice global unique namespace, and it also provides us an easy way to do deduplication to save you some space. And what we have on the right is a diagram of basically how the structure of our file system looks like. We have commit objects that represent snapshots in time, trees that represent directories, and blobs that represent files. One of the nice things about borrowing on this technique is that we can apply a lot of distributed version control system techniques to your file system. So we can merge diverging replicas, we can detect conflicts, and I should point out here that there's no real magic solution to merging files. We can merge simple line-oriented files, but for anything else, at least we can provide the user a merge base, and they'll manually do a merge at that point. And we have a lot of other convenient tools that we provide. Another important thing is just the storage layout. Objects are deduplicated, then they're compressed and stored in a log-structured file on your local file system. We also maintain an index that's used to provide a layer of indirection and speed up lookups. So now we can talk about replication. So think about users today. There's 3 main things that they do that replication can replace. So the first is backup. We back up our files onto an external disk or to a NAS device. We also use central files, some kind of centralized file storage, this could be Dropbox, to store our data in a central point. And another thing that we often do is we SCP or rsync or airdrop files between our computers. But the simple thing to do is just replicate your data between your computers. Make all your data available on your laptop and your desktop. You can also replicate your data to your phone. And if you really don't care about privacy, you might replicate that to the cloud as well or to your company's own file server. Replication also subsumes backup. So when your laptop crashes, you can basically just get a new laptop and recover with replication. And we'll make that seem instantaneous with a special optimization we call background fetch. You can see the paper for details. And this basically makes it feel like you have that replica available to you instantly. You get started, and the data will be sent over the wire in the background until a full replica is available on that laptop. So how does replication work in Ori? So it's opportunistic. We replicate, and we try to do this over local area networks. We send all the bulk data over SSH, and we detect local devices and initiate these synchronizations by sending out UDP multicast messages on a 5-second interval. We set up a cluster name and key per user, and we've protected all these messages with the AES CBC. The deltas themselves are, deltas basically consist of these objects, a collection of objects that represent a set of snapshots in time. So you think of it as my laptop is maybe 4 versions behind of my file system, so I'll send it those 4 versions and all the objects that they need to the other host. So a nice thing is that versioning makes replication a lot easier. So you can imagine you're just sending these objects constantly between all your devices. There's a few other kind of nice things about our protocol. One is the content addressable storage. This means that we don't have to rewrite objects, so we don't spend time decompressing and recompressing objects and parsing them and rewriting them. Another thing is that we do have to maintain reference counts. We use this to reclaim space in the future, like whenever users want to save space and delete older versions of their history. And in order to make this possible, we do have to decompress just metadata, not your bulk data, just to update and maintain reference counting. Another nice thing is that based on this content addressable storage model, we can trade off storage for bandwidth. So if you think you go to a remote office and you want to access some data on your desktop at your main office, and you can, if your friend sitting near you happens to have some of that data, you could replicate that data from his machine instead of your original machine. Just as a side note, for privacy reasons, users have to opt into this and want to use this and want to share their data to help others. So this brings us now to file sharing, which this is really the mechanism how we expect users to collaborate. So replication was originally just between a single user, and now grafting is how users will actually share and collaborate on their data. So you think about today, how do users collaborate? So the first is the cloud. You put files up in the cloud and you just work on them, and in the best case, if you have a nice solution, the cloud provides you with 2 files whenever there's a conflict. Another way that people collaborate today is they send emails to each other, and the email history provides you with basically a nice version history to help users understand and merge documents. Finally, the last way that we collaborate, which should be familiar to all of us, is we have version control systems. So you can think of as Git and Mercurial as good examples. These are great because it has a way for us to detect the version history, to detect conflicts. But what's really the problem here is that you have to put the forethought to set up version control. I can't take the version history that's already in Apple Time Machine or Windows 8 file history and export it to my friend. I have to go and put the effort to set up a Git repo. So what we really want is we want the file system to manage versioning and sharing. We don't want to think about setting this up and everything that comes around that. And we also don't want users to go through insane namings. It's like, what does this even mean when people start putting final and version all over a document? So this brings us to grafting. So this is a really simplified example here. So this is the version history of 2 file systems, and Alice only has 3 versions. Bob has 2. And what we're going to do is Bob wants to access some data from Alice. So Alice has shared that data with him. And he basically transforms those changes and the data that Alice provided to him into his own repository and grafts it into the repository. So it's kind of nice because now he can actually access the history and see what changed. Not only that, we maintain links so that we know these changes came from Alice's repository. The next step is that when Bob now gets some work done and makes some changes himself, Alice can actually receive those changes as well, and she can see the history. And you can imagine how this can be applied to merges and to detecting conflicts in a more complicated model. But I just wanted to give you an idea, and you can see the paper for a little more details. So what do we do about conflicts? So first of all, we detect conflicts using the history. We automatically merge when it's possible. Otherwise, we provide data so people can do a 3-way merge. So we give them 3 files, the conflicting file, the base version, and the original. Conflicts should be fairly rare in the single user case. So when users are just replicating data, it's fairly rare because they're carrying devices with them, and we'll talk about that a little further. But conflicts are fairly likely in the grafting case. But the nice thing is that in the grafting case, things aren't automatic. Merging is a very explicit operation here. So this brings us to mobile devices. So if you think about it today, there's been a trend to moving more and more services out to the cloud. So we have iCloud, Google Drive, and all these solutions. We're moving our data out to the cloud. And not just that, sometimes even parts of the application are running in the cloud. But what's really the trend is that we should notice is that devices are getting huge. Like today, there's a phone released with 128 gigabytes of storage. Also, we have really fast networks, as I mentioned, on the local area. So this creates a really good opportunity for us to transfer information basically as users physically move between points. So when you're at home, you synchronize your data with your phone, you carry it with you to work, and the nice thing is that you've basically elected a leader. In this case, I've implicitly elected my phone as a leader. When I get to work, I synchronize my documents with my computer at work. Now, if you think about the typical American commutes about 25 minutes a day. If he or she carried 16 gigabytes of storage, that's effectively a 5 gigabits of bandwidth. And one thing to note is that, yes, there's some transfer time involved, but we can use the background fetch feature to make that seem instantaneous once you arrive at work or home. So I just want to bring you to a quote This is really not a new idea, except we're applying it in a slightly new context. So I think Andy Tenenbaum mentioned that you can never underestimate the bandwidth of just carrying a lot of tapes down a highway. And if you think today, just carrying your phone is a way to transfer tons and tons of information. So let's talk a little bit about performance in our implementation. We've broken up performance into two sections. We're going to talk about the file system benchmarks, and we're going to use file bench. And we're also going to talk about the network file system benchmark, where we're building some source code remotely. So there's a few things I'd like to point out first. First, we're going to benchmark against the Fuse loopback file system. Fuse is a user-level framework for building file system drivers. It has an added latency because IOs get sent from the kernel back to a user space driver and then back into the kernel to your local file system, whether that's X4 or UFS. So the real baseline here is the loopback file system. Another important thing is I want you to understand what's kind of happening with the in-memory data structures and on disk. So there's two things. In terms of data, we have the staging area on the right. And what it is you can think of it as a data cache, a write-back cache almost, for all the changes you've done recently until a snapshot. So all writes effectively get routed straight into your disk. In terms of FS metadata, we journal those onto the disk as well, but we keep all that information in memory and cache it, so it's a little faster to do metadata reads. So here we have the file system benchmark, file bench benchmark. These are a bunch of synthetic workloads. And what I want you to take away is that generally Ori and the loopback file system, the two bars on the right in each of the benchmarks, are performing about the same. And in fact, Ori does better in the network file system and also in the web server benchmark. The only caveat here is the var-mail benchmark, which is basically because the loopback file system does not provide fsync, so it's not crash consistent, while Ori and X4 are. Another is our remote workload. And what we have here is we have Ori, and we've compared it to NFS. So I'm going to quickly point out this is not an apples-to-apples comparison. In the NFS case, all IOs are going over the wire to the remote host. In the Ori case, which is our third bar, we've pulled over a full replica of the file system, done our compile, and pushed all the changes back. And as you see, that's at least 2x faster, or about 2x faster. In the case of Ori with BF, which stands for on-demand background fetch, this is a particular flavor of background fetch. What we're doing is, as we touch files for the first time, an application opens a file, we'll block the application, download the file to the local machine, make it available to the application, allowing the application to continue, and then at the end, we will actually push all those changes back. So nothing is downloaded initially. This is the background fetch. People instantly we get to work. So what it's cost us is between a 20 and 30% performance hit, depending if we're on this WAN case that we've tested and a LAN case. Lastly, I just want to point out we have a ton of related work in this area. I think this is clear. There's tons of work on file systems, version control, and all kinds of application-level solutions for people's data management problems. So this brings us to the lessons learned. So there's a few things. So first of all, the hardware and use cases have evolved significantly in the last 20 years, or however much you want to measure. And we really need file systems to evolve and catch up to these use cases and to the hardware technology that's available. We also think that replication is no longer something that's only viewed for enterprise solutions. This is something that should be available on everybody's computer. My laptop has enough space to store all my data. Why don't I just replicate it across all my computers? And I think within a very few short number of years, we're going to see phones that can store all our data. Another important thing is this keeping file history. This is such a useful thing that this should just be the default. Every file system, every system should just support this. Some way to give us file history for users to be better off and be able to understand what they've done and be able to repair mistakes. Next is mobile devices. And we see this as a really important point. We're creating a great opportunity here. We have fast local area networks. We have tons of storage. And these devices basically allow us to create new sneaker nets where we can transfer lots of information just by the way people move around in their daily routines. So there's a few important things of future work I want to point out. One is some kind of application support for merging on Ori. We don't yet know what this is, but we want to sort of figure out that the POSIX API is very restricted in that it's such a general purpose API, we have no way to understand what the file means. So maybe there's some way that we can integrate with the file system or provide applications a better way to integrate with Ori and do merging. Another thing is there's some API complications in POSIX also where files in Ori, when they get updated in the background, so you think you've done a graft and you merge, well, if you had Emacs or Vim open, it might not tell you that a file was modified underneath you. So we probably want a way that application systems can subscribe to file change notifications. And lastly, there's two really important things. One is, right now, grafting does not get synchronized automatically. As I said, it's an explicit operation. And I think especially as we solve these first 2 points, we'd like to see how we can integrate grafting with automatic synchronization so users can get a faster turnaround on their data when they're collaborating. And lastly is really looking at authentication. Right now, we don't really do anything great around grafting and how users sort of control what they share and with who. So we want to make an easier way for users to do that. So at this point, I'll take any questions. And please visit the website if you want to download the code. We have it already added to a few package managers. And you can see the paper for additional details. Talking here.
So Jeff Canning, Harvey Mudd College. This is really cool stuff. It's really nice, and I want it. But I'm reminded of a couple of paper titles from around 10 years ago. The first one was Elephant, the file system that never forgets. And the second one was deciding when to forget in the Elephant file system. Version control is really neat, but automatically version controlling every single file, especially automatically controlled files, tends to fill up your disk. So have you guys thought about that?
So right now we have a basic policy of how we delete older snapshots. So basically as time goes on, we delete where the snapshots are sort of sparser. And we've based it on just basically looking at backup solutions today, looking at what Apple's doing with Time Machine and other kind of versioned backup solutions. And we think they're kind of sane defaults for now. But I think there's clearly like future work to be done there. Thanks.
Akshat and EC Labs. I guess it's a kind of related question. What is the policy for deciding when to create a snapshot? Because it seems to me that the performance will be highly dependent on that.
So right now, it's basically time-based. So we create snapshots periodically, and you can change it. I actually took it out, but in terms of creating snapshots, it's actually fairly fast in Ori. We measured it against a git commit, add and commit, or versus ZFS, and the performance is fairly comparable. So it's actually a fairly lightweight operation, and I think we could do a lot better job if we move the staging area to in-memory, so we could construct the snapshot in memory and just dump it on disk with a single write, which is basically how real copy-on-write file systems like ZFS and Waffle do it. So I think we could make that a lot cheaper than it is today. So I'm actually not very worried about it.
Well, I mean, time-wise, it probably won't be a problem, but just when you're doing the synchronization, the more snapshots you have, the longer it's going to take to synchronize, right?
Sure. We also prioritize, though, what we synchronize, right? Users care more about their most recent versions. So, you know, when I think about it, I'm working on my laptop. I want to make sure that the latest version of my file is available on my desktop. When a laptop disconnects, if the history is sort of sparse and hasn't been filled in yet, I'm not super bummed out by that, right?
Sidney Amani from Nectar. So you mentioned a couple of times that you keep some metadata in memory. Have you evaluated how much memory overhead you have? And do you think it's going to scale if I was to use that file system for my entire file system?
I don't have exact numbers off the top of my head, but each entry sort of per file that is being cached in memory of that metadata is very small. It's on the order of a couple hundred bytes. And what I've seen like with personal data that I've been storing in Ori, it's only really adding tens of megabytes. Like I'm actually getting Ori right now working on my phone.
Can you please clarify what metadata exactly you store in memory?
So you can think of basically like a directory cache, the same way you have directory cache in Linux, and also basically caching the fstat structures. So everything you get with fstat, the file size, the chmod bits, and all, and that stuff. Is that clear? Yep. Cool. Thanks.
Hi, Jason Flynn from Michigan. So I think I agree with all of your design principles except for one, and that is when I look at the computers that are out there, there's fairly substantial differences between a mobile device and a server class machine in terms of availability, battery energy, and so on. And it feels like you're trying to fit them all in the same box. And I think the strength of some of the centralized systems that you mentioned are that they adjust what each machine is asked to do according to the capabilities of those machines. And so really the question I have is, wouldn't it be better to go back and at least take advantage of the capabilities of each machine according to what it can provide, rather than trying to make everything look the same?
So I think that the disparity between devices is really getting smaller and smaller. You know, if I go and buy a laptop with Flash is so expensive that it's going to be only a factor of, like less than 10 now between a phone and my laptop. So I think what really happens and what we're trying to do with Ori is basically a matter of how we prune the history. So your mobile phone's not going to keep the history for a year. It's going to keep a very short history, and maybe even just like the latest version plus whatever you've worked on in the last week. While your laptop might keep history for 2-3 years, and your desktop maybe even longer. So I think like degrading gracefully is a nice idea, especially given that the trend is that mobile devices will have lots of space. Thanks.
Okay, this will be the last question.
Matthew Fernandez from NICTA and UNSW. In my experience, non-technical users, regardless of what tool you give them, do not enjoy resolving merge conflicts. So do you think forcing them to do these resolutions is the way to go when services like Dropbox and similar just rename the files?
So I think that's true, and there are a lot of like startups going into this like for PowerPoint and Word. So it's kind of like not something I see as like an interesting research problem for me per se, but I think it's valid, but I think people's lives would be better if they at least had like a base to look at, if they at least have some context to understand how to do a merge. So if you have just two documents telling you, here's these two files and they're conflicting, that's really not super useful to users. But if you say like, this person was working off this version and these are the changes they did, that's useful. And once you have three-way merges and you support that, you can implement tools, I think, to do something a little better, right? But I mean, I think I agree with you though. Like, I think there's no good solution how to do this for movies or images, and at that point, like, it's whatever the user can do.
Okay,
I
thanks.
think it's a valid point. Thank you.
Next speaker.